So I plug in for these things, and I'm like, oh, well, this term, what's them next? This is next. This term is like, these three have x squares. I'm like, okay, well, just group it by whether they have x's or not. And then I'm like, oh, this one is next, and I know it's going to be equal to that. So it's going to be equal to that. The second term is the only one for next. If I see a way where I can simplify things, I like that. This. And the monster thing is
So how about to get started, let me try with two humorous anecdotes that hopefully will put us all in a good mood if I tell these correctly. Both, I won't exaggerate either of them. So I was a student. I can't quite recall what the class was, something like circuit theory. The guy teaching it was grumpy. He taught well, but he'd come in, he was never in a particularly good mood. He was kind of mean, just in the way that he responded to students. It was an absolutely quiet, dead classroom, not a sound. And the professor was facing the board writing. And somebody folded a paper airplane, just a conventional paper airplane, and from the back of the classroom, threw it. And everybody kind of watched as it drifted across the classroom. And the professor turns to face the classroom, and the plane hits him right in the nose. And he got very angry. He got really angry, which contributed to how funny it was. But also, when you think of it, what are the odds of this happening? Like, I mean, you could try this 10,000 times, and you would not get that to work, right? Meaning...
You're inviting me to try is what you're saying.
Well, by all means, throw paper airplanes, but see if you can get one within 10 feet of me, and I'll be impressed. And because it wasn't a straight line plane. It wasn't, it had the flaps on it, so it drifted. Anyway, I'll save the other anecdote for some other time. Okay, so I think most of you grew up in the U.S., or perhaps half of you grew up in the U.S., and those of you who grew up elsewhere, probably times have changed. But when I was a kid, I went to public school in France for the first 3 grades. And teachers were so mean there. It was kind of like the British system. They were just as mean in French. But there was real physical threats. So the teacher, she'd walk around with a big wooden ruler, and if you weren't paying attention, that ruler would come down, and would come down basically aiming for your hands or your fingers, sometimes coming real close. So things are different now. Paper airplanes, I guess, would be construed as abuse on the part of the student if you started throwing this thing. Okay. So where we were at last time is just discussing how, given a set of chemical reactions, and I apologize, I was too lazy to switch over to Windows PC here, so the fonts are messed up. I don't think it'll distract us too much. So what we were discussing was, given a set of chemical reactions, so given a set of chemical reactions that these, according to my view, just describe rules about how molecular types combine to form other types, and given information about the relative rates, 1, 2, and 3, we can analyze how such a system would behave. We can analyze it in the sense that given initial quantities or initial concentrations of the types A, B, and C, we can track how those quantities or concentrations will change. So just to bring us back up to speed, how about a new victim? How about, I've called upon you before, with the red hair, what's your name? Ryan. Too many Ryans. Talk to us a little bit. Given initial quantities or concentrations of A, B, and C, how can you track over time how those quantities will change? How would you go about doing it?
It's kind of like a search tree in AI, kind of like you know the probability of
Okay,
what
yeah.
happening.
Yeah.
And you just adjust your probabilities and continue on.
Perfect. So that's the view where what we do is we say, all right, we're at time 0. At time 0, we have quantities of A, B, and C, let's say of 5, 5, and 5. We should also talk about concentrations, but let's assume that we have 5 molecules of A, 5 of B, and 5 of C. Then we have these 3 reactions that can fire. So let's call this R1, R2, and R3. So what we can do is we can compute what is the probability that R1 is the next to fire. So here, this is the probability that at time 0, something's going to happen next. And suppose that reaction R1 is the next to fire. Well, let's compute that probability. Let's say it's 0.3. Versus the probability that R2 is the next to fire. Let's say that's 0.2. Versus the probability that R3 is the next to fire. Let's say that's 0.5. So these will be a probability distribution on the next event. Given that calculation, as Ryan suggested, what we can do is simply sample that probability. I'll be talking a bit about sampling probabilities in a moment. But basically, we'll choose at random which of these 3 reactions happen. But we'll choose at random based upon the probabilities that we've computed. Based upon that random choice, we decide, let's say, that reaction R3 fired. So we'll see in a moment, we didn't necessarily decide that R3 fired because it was the most probable. It just happened that way. But once R3 fires, what does that mean? Well, it means we have 1 less of A, 1 less of C, and 2 more of B. So we update the quantities. 1 less of A is 4, 1 less of C is 4, and 2 more of B is 6. So now we've got new 7. So now we've got new quantities. Based upon new quantities, we'll calculate new probabilities. Given new probabilities, we can again repeat the process. And we can just keep going. So Ryan, when does the process stop?
When none of the reactions can fire, or
when
when it at least stabilizes.
Yeah. But that's not guaranteed to happen, right? But talk to us a bit more. So when none of the reactions can fire, when can we arrive at a situation when none of the reactions can fire?
When there's just one time left.
Yeah. Or suppose that we have 0 of A and 0 of C, or just 0 of A is sufficient to kill this one. So if we have 0 of A and 0 of B, then we're done. But it's possible that this never happens, depending upon the set of reactions. It's possible that we just continue this process and it continues indefinitely. And that's not physically implausible. It simply means that the chemical reactions continue running. So the stopping criteria is going to be of interest. Now, the conventional way that people simulate such systems is they don't really focus on the stopping criteria. Instead, they just say, we're going to characterize how this behaves as a function of time for some amount of time that we're interested in. That's a valid thing to do. But, as I'll try to explain in a moment, a different twist on it is to focus on the outcome and not to focus on a particular time interval. All right. But just quickly to remind us, okay, another stupid joke. There's a famous professor. His name is Professor Wilson. He's a mathematician. And he's in the post office. And he's standing in the post office, stroking his beard, deep in thought. The student walks into the post office, recognizes the famous professor. And so there's the famous professor. And he just waits and he waits and he waits. The postal clerk is waiting. They're waiting 20 minutes as he's stroking his beard. So finally the student musters the courage and says, "Excuse me, Professor Wilson." And he says, "Wilson, that's the name." And then he writes it down. He forgot his own name. At least I got a chuckle. So I can't remember your name in the plaid shirt. It's Jacob. All right. Why couldn't I remember that? So Jacob, what is the other way of characterizing a set of chemical reactions? And talk to us a bit about differential equations. So why differential equations, and when would differential equations be applicable?
Differential equations because there's different quantities that are changing over time.
Uh-huh.
The change in one of them depends on the rates of the other one.
Right. And so each reaction, if it's a rule, it specifies how molecular types combine to form other types at a certain rate. So that means that the concentrations of these molecular types are changing as a function of time at a certain rate. That immediately gives us a differential equation interpretation. So that's the other way to view it. But let's talk a little bit more about what's called stochastic simulation. And this is the view that Ryan suggested, which is let's compute probabilities and let's track the simulation at the level of individual reactions firing as a function of time or the number of steps. So here, I hope these slides aren't too messed up. Let's say we have 555. 3 possible reactions that can happen, R1, R2, and R3. And so, again, this is going to be completely messed up, but maybe this is good. Now you'll have to tell me, wow, the Mercedes symbol, how did that come in there? But does anyone know, I did a little bit of a Google search, does anyone know how I can take PowerPoint slides created with the latest version of PowerPoint and make them work in a Mac variant? I don't know what's wrong. I don't feel like reformatting all the equations. And the problem, well, I can, but it's all animated. You know, I bring things in one at a time. So I could save it all to, maybe that's not a bad idea. But then just give up on PowerPoint entirely. But, look,
Doesn't the PowerPoint software in Mac have an equation builder?
It does, but if I built the equations in Microsoft, for whatever reason, there seems no way to export the slides with them without... that's what I used to do. So I used to run VMware on this machine. But, and I can do that again, but I have huge problems with the machine hanging. And there's nothing worse than standing in front of a crowd and have the machine just hang. Okay, anyways, enough of that. That's a good idea, but will the Google Doc, will it preserve animations, or how does it display PowerPoint? Does it do it well? I should give... Yeah, okay. All right. I don't know if it does it any worse than this. So silver linings here. Now that it's not on the screen, Chris, right? Alex. So tell us what should be properly displayed here. How do we compute the probability that reaction I is the next one to fire? As a function of the quantities of x1, x2, x3, and the rates k, or given what's here.
Something to do with that specific reaction divided by the summation of the other ones.
Yeah, but what to do specifically with the reaction? So let's compute an alpha 1. What is alpha 1 going to be?
I'm not sure.
It's going to be, let's call this K1, K2, K3. So alpha 1 is going to be K1. Why? Because we're computing exactly as Alex suggested, the alpha with respect to the first reaction. So K1 times the quantity of A. But in fact, what we'll do is the quantity of A, choose 2, which is, as we went through last time, the number of ways of choosing 2 molecules out of the total number of molecules of A we have, times the number of molecules of B that we have. So each alpha is just the rate constant, the value of K that we associate with the reaction, times the quantity of the reactants present. If there's a coefficient greater than 1, then it's the quantities of the reactants present choose the number of items that are the coefficient. So that's how we construct the alphas. Is everybody okay with that? Then what is probability of R1? Probability of R1 is going to be alpha 1 over alpha 1 plus alpha 2 plus alpha 3. Or, of course, we compute alpha 2 and alpha 3 in the same way for reactions R2 and R3. So that's how we compute the probabilities here for 0.3, 0.2, 0.5, let's say, in a given step. Let's ignore time for the time being, pun intended. But let me just say this. So as I started to explain last time, this entire paradigm of simulating a set of chemical reactions as a sequence of discrete events was controversial when it was proposed 30 years ago. And the controversy, in a sense, was legitimate. Because what we're suggesting here is that we can track the evolution of a system like this by computing a sequence of probabilities of discrete events happening. But those discrete events are not mutually exclusive events, in the sense that if we have a large collection of molecules, A, B, and C, what's to say that reaction R1 and R2 can't be firing simultaneously? Or what's to say that the reaction R1, we can't have that rule firing 10,000 times simultaneously with separate molecules of A and B in our system? So you may object to saying that we've got a big system. How can we even speak of the probability of the next reaction happening when many reactions can happen simultaneously? So any thoughts on that? Yes, what's your name? Rohan.
I guess if you consider a system with 15 molecules,
Yeah.
then it's not as big of a deal as if you consider something like a normal chemical system has somewhere of the order of like 10 to the 23rd particle.
Yeah.
When definitely 2 reactions are happening at the same time. But in this case, with 15 molecules, they can see the assumption that 2 aren't.
Yeah. So that's a very good response. I agree with that. But the interesting part is that this view, and it was Dan Gillespie who proposed it, is in fact mathematically correct, and from a theoretical perspective on how to simulate a set of chemical reactions, is actually the correct way to approach things. It's, as you guys know, if you've taken courses, and you all have on physics and calculus, the notion of something being infinitesimally small or infinitely large, these are very abstract concepts. And some people like me instinctively dislike those concepts. Maybe this is why I chose computer engineering as a profession, because 0 versus 1, this feels like a white rock or a black rock that I can hold in my hand. I can understand what a white rock is or what a black rock is, what 0 and 1 is. I don't really understand what an infinitesimal increment is when I'm integrating. But nonetheless, that's just my ignorance or my bias. The concepts of infinitely small or infinitely large or an infinitely small time slice, these turn out to be very useful concepts in terms of what we can calculate. There's a famous saying which has been repeated and misattributed to many people, and that's that all models in science and engineering are wrong, but some of them are useful. So instead of debating what is the nature of reality, simply calculus is useful. So this notion that we're going to say that there is some next reaction that is the next reaction to fire, it turns out that based upon pure rigorous mathematics, you can then derive a proper characterization of what happens to a collection of molecules. And so in a paper which I put as assigned reading, I don't know if it's assigned reading because it is very mathematical, but a paper on the website that is by Dan Gillespie, and it's called an exact simulation of chemical systems. It's a long paper, a difficult one to read, but it's one where starting with physics and starting with the so-called billiard ball model of chemical kinetics, and that's the model where you view molecules just as hard spheres bouncing around, and a reaction occurring when molecules collide with a certain probability. So when they collide with a certain probability, depending upon the stickiness, a reaction happens or doesn't. But based upon that, you can derive what mathematical chemists then have as their standard framework, which happens to match the way differential equations operate for large quantities, with certain exceptions. And those exceptions I'm going to focus on. Can anyone suggest what is an exception? So when could the model of a differential equation simply be wrong? Yes, Stuart.
When we're talking about the very small time slices?
Yeah, certainly. But what I'm interested in, and I'm going to try to get to this, I should speed it up in today's lecture, is a situation where even if you have a large number of molecules, and even if you're not concerned about small time slices, if you try to analyze your system or simulate it with differential equations, you're simply going to get the wrong answer. When could that be?
When you don't have enough molecules for a certain reaction, the differential equation, it'll just divide the quantities smaller.
That's true. So when, a differential equation model assumes a continuous value for the concentrations. And this means that it can go to a concentration that's less than one molecule. You mean, that's true. And perhaps to an extent that'll be the heart of what I'm suggesting, but maybe not. So, Michelle?
Is it when they're not mixed up?
When they're not mixed up, that's certainly the case. But then you could, and when they're not mixed up, meaning that you can't just assume that you're in a bucket or in a test tube where each reaction is equally likely. But there's something else that I'm going at.
A discontinuity in math that doesn't happen for some time, then it starts happening.
So not that. So what is the theme that I keep returning to in the course? Yeah, Rohan, do you have it?
I was about to say just that when you talk about continuous, it's not exactly continuous if you're dealing with such small scales of molecules. 16 versus 15 is big, but much more discontinuous than like 6.02 or 1.
These are all good suggestions, but I'm trying to pull this out of you. Maybe I shouldn't try so hard. French has lots of, in a sense, French, the expressions that are in common usage, they're more graphic than the expressions in English. So there's one that's translated, it means that I'm pulling the worms from your nose, which I don't know what that means, but it means that I'm trying to get something from you. So I'm trying too hard to pull worms from your noses. So here, what I'm going to sketch, I drew this doodle last time, so I won't exaggerate it this time. But suppose that we start in some state. And imagine that it's not 555 necessarily. Imagine that we could have a large number of molecules here. But given some starting state, imagine now that when I draw a trajectory, what I mean by this is I'm illustrating where we go from a given point. So now when I talk about points in space, imagine we've got the space consisting of, if we have 3 molecular types, it'll be 3-dimensional space, so 3 coordinates, where along each coordinate, the point represents the quantity or the concentration. So when I go to a new point, this is a new point in the space with 3 types, 3-dimensional space, with n types, n-dimensional space. But imagine that I'm following such a trajectory through the space. This is a particular trajectory that I follow if the sequence of reactions, the specific sequence of reactions that I tracked in the simulation occurs, meaning that I've executed, let's say, R1 followed by R2, followed by R2, followed by R2, followed by R1, followed by R3. So a specific sequence of reactions takes me in some direction in the state space. And that's one particular trajectory, which in a sense models one possibility in terms of the sequence of reactions that I can get. So, Ryan, I do that. But what does this tell me?
It tells you that if you do, like if those specific things happen, that's where it'll end up.
But what if next time I go this way?
That's probably equally likely.
That's equally likely. But so what do I do in order to characterize the system?
Characterize where you think it'll end up?
Yeah. So the differential equation model is I take this set of chemical reactions, translate it to a set of differential equations, and then simulate the differential equations, either myself or I use MATLAB. What does it do? It gives me, as a function of time, the concentrations of A, B, and C. Here, what am I getting?
You get a bunch of the different possible outcomes. But I guess to figure out which ones are most likely, you'd have to run through it a bunch of times and see what...
Exactly. So what you have to do is, you don't do this once. You don't generate a trajectory once. You generate many, many trajectories. You generate enough trajectories so that you can get a statistical estimate of what's going on. So you generate this once, you generate another one, 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 generate lots. For a system like this, you guys will be asked to do this on the next homework assignment. For a system like this, maybe 1,000, maybe 10,000, depending upon the precision of the values that you want to compute. But what's interesting is, suppose that I do 1,000 simulations. And suppose that I get a bunch going off here and a bunch going off here. So after, let's say, 1,000 steps, I'm somewhere here or I'm somewhere here. Then this is giving me information about how the system behaves. What kind of information? Well, it's suggesting that you can call this a bimodal response, if you guys are comfortable with that kind of jargon. But it means in terms of, well, let me try to plot this more concretely. So, this is time. But for time, we'll just assume that it's the number of steps, so the number of reactions that have fired after one time step, so we have discrete time steps. But as a function of time, we can look at what is the expected quantity of A that we have. So we'll have a separate graph like this for each molecular type in our system. At time 0, let's say we're at 5. Then what will we get at time 1, 2, 3, 4, 5? Well, so Jacob or Ryan, what should I plot here at time 1?
Whatever the amount of A is on average.
On average. That's the critical part. So what I want to do here is plot the value of A on average. So I've done 1,000 trials, and I take the average value of A that I have at step 1. Obviously, at step 1, after a few steps, I won't have much of a divergence. But after a lot of steps, I can begin to have a divergence. But I've actually lost some information there. So what information have I lost? I've lost the fact that I'm averaging out the value of A. And this is what the differential equation does, in essence. It takes the average. But in fact, in separate trajectories, what I can get is I can have A always clustering over here, which might be A in the value. Instead of this, let's go for bigger values. So let's go for 5,000. So let's say here, the final value of A is between 800 and 1,000, or the value of A. And over here, it's between 10,000 and 20,000. And so the value of A somehow always seems to be roughly around 1,000, or it seems to be bigger than 10,000. But it never seems to be over here in the center. Then I've lost that information if I'm simply averaging out the results. So if I simply plot the value of A as a function of time by the averaging, I've lost this information. I've lost this information if I do a differential equation. But the point is, if I'm doing a stochastic simulation, I don't have to lose this information. I can compute this information. OK. I think that I went into this little digression, and I'll return to it properly. But I went into this little digression in the first or second lecture, where I talked to you about a virus, right? Does anybody remember that? Can anyone vaguely even repeat what I talked about, Jordan?
I can't remember what the virus was called, but it was essentially, it decided on two modes based on
Yeah.
the conditions of the environment was to either take over the host cell or to remain dormant within the DNA.
Right. Perfect. So it was called a macrophage. So this is a virus that attacks the bacteria. And just as Jordan described, it's two different behaviors that the virus chooses. One behavior is to be stealthy and incorporate your genetic material with the material of the host bacterium, or the hijack mode, where you simply destroy the bacterium and launch copies of yourself into the environment. So that's one of two possibilities. And it seemed to be making that choice randomly. And the argument is that it's making that random choice through chemical reactions. Well, what else could it be? How else could it be making that random choice? And I'll show you guys the set of chemical reactions, the so-called circuit, to make that decision. But it's a circuit that, if you write down the set of chemical reactions and try to simulate them with differential equations, well, you'll just get the average value. And if you get the average value, then the virus always decides to do something that's neither outcome. Whereas if you simulate it stochastically this way, and you do a proper statistical separation in terms of what's going on, you can actually understand what's going on. But any comments on this? So, Jesse, do you buy the argument that for situations like that, even though we're not necessarily talking about very, very small amounts, that we have to do things stochastically? Yeah?
I buy that. I mean, the idea of losing information makes a lot of sense. It would make sense to do things stochastically and with probabilities than to just compute differential equations.
But you can see that before this was proposed and before people had powerful computers, the notion that you could track individual reactions firing in order to simulate a system of certain size seems preposterous. You know, how can you, because that's what you're doing with the stochastic simulation. You're tracking individual reactions firing. And before there was the understanding of a probabilistic distribution in discrete outcomes, you might have said, well, what's the point of doing it that way? Let's just compute the rate of change and do a proper simulation based upon the rate of change. But I think that there is validity here. But controversy remains within the community of people who are acquainted with the chemistry, but also deal with the mathematics. I'll return to that in a moment, but let me forge ahead. I'm trying to decide if I should talk about something boring or something about exciting next. Okay. Logically, I'll talk about what's boring next, but keep this in mind. because we'll be talking about obtaining distinct probabilistic outcomes in a very specific way. So in a bit, I'm going to show you a set of chemical reactions that is much more extreme than this in terms of distinct outcomes. And it's just setting up an artificial set of reactions. Yes, what's your name?
Vishwesh. I just want to
Vishwesh.
get this idea. Each those states are states where the probabilities converge.
They don't necessarily converge.
So they're never steady, or?
Well, that's actually a very good question. So this was the question before. When do things end? They end from a simulation perspective when you're tired of running your simulation. So you run it, and you simply say, okay, enough. Control-C, end of simulation. Or they end when you define some stopping criteria, which is, let's say, number of steps that you go forward. Or they end when no further reactions are possible, as Ryan suggested, where, let's say, you have 0 of a certain quantity. That's a bit unrealistic because in a large system, you never actually go to 0. Yes, Jordan?
With this large system, could you make it a parameter so that the possibility of or the rate of reaction would be so slow that it might as well be 0?
Well, essentially, that's what happens when you go to low quantities or low concentrations. If you think about it, the probability of a reaction firing is proportional to K, but it's also proportional to the quantity of the reactants that you have. And so when your quantities or concentrations drop, the probability of a reaction drops to nearly 0. Does that make sense? Yeah. But to answer your question, Bishwesh with a B, right? That's one possibility. But another possibility is that it reaches equilibrium. But it reaches equilibrium over here, which means the reactions continue firing, but it just spends its time over here. Another possibility is that it reaches equilibrium, but it reaches equilibrium over here. And in fact, that's the really interesting case, for instance, with the virus, because the set of chemical reactions takes you to an equilibrium point here. And that equilibrium point is what characterizes the stealth mode. Or it takes you to an equilibrium here, which characterizes what happens in the hijack mode. And the chemistry was designed by evolution to take us into 2 distinct directions with very distinct outcomes in terms of what happens that are stable. Make sense? Yeah. Go ahead.
I was just going to say, this kind of looks like behavior you would see in when you're dealing with nonlinear dynamics.
Yeah.
Like multiple steady states.
Yeah, that's exactly what it is. So part of the community that studies chemical reactions from an abstract mathematical point of view are mathematicians who are interested in nonlinear dynamics. And what's interesting here, it's beyond the scope of this course and beyond my expertise, but in a sense, really interesting branches of mathematics have been developed as a result of this particular model. So it goes back 50 years where people have started studying complicated chemical reactions and the dynamics of them and, as you said, nonlinear dynamics giving us different stable states or potentially having unstable states. So all of that comes into play. Okay. Let me switch to something that's boring. It's boring because, as I started to suggest last time, I'm not really that interested in algorithmic techniques for simulating a set of chemical reactions. But here is going to be a sequence of ideas on how we can simulate a set of chemical reactions. So let me step through that. So as I attempted to doodle last time, this would be a typical trajectory that we might follow in a set of chemical reactions. So a trajectory would go somewhere, and then we go back. And then we go back. So what I'm trying to indicate is that there is some kind of notion of forward progress. The set of reactions they fire, but because it's a coupled set of reactions, it takes us forward and backwards in the state space, meaning for the different quantities, they both increase and decrease along different coordinates. This makes sense, for instance, if we do have reverse reactions in our system, then if the probability of the reverse reaction isn't that much less than that of the forward reaction, then sometimes we go forward, sometimes we go backwards. Sometimes we go forward, sometimes we go backwards. But even if we have reactions that are strongly biased in the forward direction, if they're coupled, meaning if we have products that are reactants in our system, and in fact, suppose that every product is also a reactant, that means that reactions can fire that increase a given quantity, and other reactions can fire that can decrease it. So you would expect there to be a seesaw-type behavior along all your coordinates. So you would expect this type of behavior. If the system simply achieves some kind of equilibrium immediately, then perhaps it's not interesting. So interesting systems are systems that compute something. So they have the seesaw along all the coordinates, but they go somewhere in terms of what values they compute. But in terms of the algorithm that we would program to achieve this, well, if you think about this, we will spend a lot of our time doing exactly what we've been discussing, which is computing probabilities, sampling the probability distribution, picking one reaction, changing the quantities, recomputing the probabilities, sampling the probabilities, choosing a reaction, updating the quantities, and we keep doing that. So the idea that I'd like to suggest and discuss is what happens if we try to be more clever about it. So in this particular case, suppose that the sequence of reactions that takes us from S2 to S3 to S4 back to S2, suppose that's a very high probability. So suppose we're in state S2. The probability of that given transition is 99.99. Probability of this transition is 0.99. And so then we'll end up staying in the cycle for a long time. Any ideas on what we can do to expedite the simulations? Do we have no choice? Do we simply have to cycle around? Chris? She's shaking.
Last time, no, you can like break and
Okay, perfect. But how can you break out?
how?
Yeah, just break out. So do you guys remember the, pardon me?
Break semicolon and move on.
That's good. I like that. Because when you're writing code, you can do this. But the point is that what we're doing is we're tracking the probabilities very carefully. Because if you think of this, if we're loose about the probability calculations at any point, then quickly we'll just lose all meaning in what we're simulating. So, we have to track the probabilities of the events happening and follow them very precisely. And so if we're just tired of being in a loop, it's true that if we're in an infinite loop, so if there's no way to break out, then we're just in an equilibrium, and so then, as Chris suggested, just kill the simulation algorithmically. But suppose it's not. So suppose that the probability of this happening is small, exiting the loop, but it's not zero. Then how do we just break out of the loop? Where do we go next? What do we do? So any ideas on this?
Choose the one with low probability and take the high probability.
So
We know that we are going to loop,
so we know that we're going to loop. So
so we choose the other one.
we choose the other one, but we choose it and we just go in that direction? Any ideas? Yes, yeah?
I think there's a certain probability of complete single loop.
Yeah.
And
Perfect.
You can do this many times. And you multiple them together. There should be another loop for the other direction.
Perfect. So what I was suggesting, oops. So far, so good. I'm just seeing how bad the fonts are. Okay. So far, so good. So this is going to be a highly contrived example to illustrate what's going on, but in fact, the method generalizes. Here's the idea that I'm just repeating exactly what Yale said. If we find ourselves in a loop, meaning we've gone through a sequence of states and we've come back to where we're at, well, obviously, there is a probability that we're going to do the same thing again. We're going to go again through that same loop. There's a probability we'll do it again and again and again, perhaps many times. But there's also a probability that we're going to exit the loop, right? So from each given state, there's the probability that we continue on the path that will keep us on the loop, or there's the probability that we'll take some other branch, and that'll take us outside of the loop. Of course, we could be on another loop at that point. But it's meaningful to talk about the probability of staying in a loop versus exiting the loop. And that's exactly what we're going to focus on. We're going to say, if there's a loop, we can do is we can be blind and stupid about it in our simulation and simply follow the loop, doing our calculations, computing the probabilities, the same set of probabilities, over and over again, and following the loop. Or what we can do is say, let's identify the loop. Let's try to characterize the probability of staying in the loop versus the probability of exiting the loop. And then what we can do is we can sample that probability distribution. So recall what we're doing is we're saying at a given point in time, we compute what is the probability of each reaction happening, and then we choose one. We can generalize the concept to saying what is the probability of staying in a loop versus exiting a loop. And if we do the calculation properly, we're computing exactly the same thing. It's exactly the same overall effect. Okay, let me illustrate. Now, the illustration here, it's set up so it's a highly contrived set of reactions in every sense. I don't know how effective it is, but let's step through it. So suppose we have the set of reactions A plus N goes to B, B plus N goes to C, and C goes to A plus 2N. The N there that I put in is completely irrelevant. I put that in so that these look like reactions, literally. Because if I just said A goes to B, B goes to C, and C goes to A, then it doesn't look like reactions anymore. Forget about the N. That's just there for visual appeal. Was there a question? Okay, but there's two other reactions. There's B goes to X and C goes to Y. So in terms of the structure, I think I have this on the next slide. What I have is I have the state A, B, C, and then I have exiting at X, exiting at Y. Now here's the highly contrived part. Suppose that I had just a single molecule of A to begin with. Then what's going to happen? So Jack, what's going to happen if I have a single molecule of A? What could happen?
You'll continue around in a loop until you get either an X or Y.
Right. So the only thing that can happen if I have a single molecule of A is I can go to a single molecule of B. If I have a single molecule of B, two things can happen. I can either get a single molecule of X, in which case I've exited the loop, or I can get a single molecule of C, in which the game is still on. Let's go with a race car mentality where we're Grand Prix, you're racing around. If you crash, you crash. So if you crash at point X, you're out of the race. But you can continue in the race. So you can go from A to B to C to A to B to C to A to B to C to A to B to C. And if you're in B, you can exit at X, or if you're C, you can exit at Y. But the point is, given the information on the screen, we should be able to calculate things. So what can we calculate? Yeah.
When it takes a very small time interval, there's a very little chance to get out of the loop. So we can just assume that they will stay in the loop, and we can just see it as a register or just a delay. And after it's after one cycle of the clock, maybe one cycle of that loop, we input some certain type of molecules. This is like how to build a finite state machine, and will output SX or SY.
So I'm not sure if I followed all of that. It's very interesting creative thinking. So you're suggesting we should treat this as a finite state machine. But let's keep it simpler here. Because what I'm going at is, based upon what I told you poorly in terms of how we compute the alphas and so forth, we can calculate everything on the screen. Yeah, so Rohan?
So I guess this is a stochastic thing, so I think of it as like a Markov chain. You can model this process like
Perfect.
that. And if you set up something like a Markov chain, you can calculate the probability of like A going to X eventually, the expected number of times it takes to go from A to X.
So that's exactly what I want to do, but without invoking, it's certainly a Markov chain, and we could invoke Markov theory, but let's just do it. Let's just sit down and calculate it. So how could we do this? Yeah, go.
You have to set up like a system of equations where you say that the expected number, or what are we calculating? Is it the probability or what?
But that's what's interesting here. So this is the insight here. But what we're going to do is to calculate the probability of staying in the loop versus exiting the loop. But first, and I'm afraid the fonts are going to be messed up here. But first, let's step through and compute the individual probabilities. And computing the individual probabilities, there's nothing to it. We know how to do it. But I think here, what I try to illustrate is what's going on. So suppose that you were paying for supercomputing time to simulate this system. Here's what you would do. You would conduct many trials. So as we discussed before, you don't characterize your system by following one trajectory from beginning to end. You characterize your system by following a trajectory from beginning to end, and then doing it 10,000 times. So let's call these trials. For trial 1, here's what you'd do. You'd simulate it, which means, by the way, if you've noticed the way I've set up the reactions, the reaction rates for exiting are much, much smaller than the reaction rates for staying in the loop, right? So everything is symmetric here, meaning the probability is just the number of molecules which we're assuming we have is 1 times the different reactions. But if the reaction rates are 3 orders of magnitude smaller for the B and C going to X and Y reactions, it means we're likely to cycle around perhaps 1,000 times until randomly we exit or X at X and Y. So that's one simulation. But then, of course, to get a sample of this, we'd have to do perhaps 10,000. So if I had set this up properly for this slide, I would have said, all right, I want you to go and calculate the probability of exiting an X versus Y. And if you set up your computer code to do it, you'd have to do perhaps 10,000, maybe even more, 100,000 simulations of this. And that seems like overkill. We should be able to calculate it. So that's where I'm going. So to calculate it, what can we do? Well, let's be pedantic about it. Let's just begin calculating it. Sorry. Here, the fonts are going to be a bit messed up. I think I'm just going to miss the arithmetic signs. So suppose that we start in state SA. What is the probability of going to state SB? Well, it's 1. Nothing else can happen. That's what's going to happen next. But then when we're in state SB, 2 things can happen. We can stay in the loop with some probability P, or we can exit the loop with probability 1 minus P. So like the rest of you, I was too lazy to compute P for these slides, but we could compute P. Someone step us through. So Ron, how would you actually compute P here?
So it says that the probability is B equal to X is 0.01.
Well, that's the rate constant, but close enough.
Oh.
Okay. But what we would have to do is take the quantities of A, B, and C, B and X. For each one of those reactions, compute an alpha. The alpha is going to be the rate constant, either 1, 2, 3, or 0.001, 0.002, times the quantities present of A, B, C, and I guess N here, suppose with some quantity of N, and then compute our alpha, and then compute all of the alphas and divide by the sum of the alphas. But that's all we're doing here. You can actually do this. I'll have you do this on a quiz. But that's going to be P. It's going to be some probability P. Now, the probability of exiting here is going to be 1 minus P. There's only 2 possibilities, P or 1 minus P. Sorry, I'm missing the minus sign. Can I draw it on? P versus 1 minus P. OK, that's just computing the probabilities in one step. What comes next? Well, if we keep going, at C, there's going to be a probability Q of continuing on the loop versus a probability 1 minus Q of exiting. OK, so there's a P and there's a Q. And notice that if we come back to the start here, the way the reactions are set up, we're in exactly the same situation. So the second time around the loop, we're still going to have 1 P, Q, 1 minus P, 1 minus Q. So where do we go from there? Yeah, Jacob.
So if you stay in the loop, or the probability of staying in the loop, like if you start at SA, the probability that you'll come back to SA is P times Q.
Correct. So going around, the probability of going around the loop once is P times Q.
And then exiting, it would be 1 minus that.
Again, but that's, I want to directly compute the probability of staying in the loop versus exiting the loop. Not going around once, but for all time.
Well, you're not going to stay in the loop because eventually you're going to exit it.
Right. So that's going to be the critical assumption here, that mathematically, if you have a non-zero probability of exiting, you will eventually exit. And you can argue about this, because you could say, what if from here to infinite time, I always choose to stay on the loop? But mathematically, people who deal with probabilities will say no. If there is a non-zero probability of exiting, you will eventually exit. How do we calculate that? Because there's going to be just a formula that tells us what is the probability of exiting at x versus exiting at y. Yeah?
Sorry, just the first thing is to compute the probability of staying in the loop.
Correct. Yeah. Very good.
1 times p times q.
Correct. That's the probability of staying in the loop. Versus exiting is what?
Yeah, and you just...
But what is the probability of exiting the first time around?
1 minus p times 1 minus q.
Well, it's actually going to be 1 minus p,
1 minus p plus 1 minus p.
and then p times 1 minus q. So the probability of exiting at x the first time around is going to be 1 times 1 minus p. The probability of exiting at y is going to be 1 times p times 1 minus q. So that's two probabilities, right? Okay. So where do we go?
Raise it and then
Raise it to a power. Okay, that's one guess. John.
keep adding terms like going around. So the first exiting on the first one was 1 times 1 minus p.
Yeah.
The second one was 1 times p times 1 minus q. And then you can go around again and do 1 times p times q times the 1 minus p to get to it the second time.
Yeah.
And then you can just keep doing that, and you'll get an infinite series, and
Yeah.
you can probably do with it somehow.
Yeah, that's a good suggestion. But I'm too lazy to do that. So what I want to do is to reason because if you did that, this would be an interesting exercise. You would hopefully get the answer that I'm going to show you. But I want to get the answer just by reasoning what the answer should be. And I want to get it just, instead of raising it to a power, which is a good suggestion, John, because you're thinking, what is the probability? Just accept this argument. When I've gone around the loop once, here, everything is exactly as it was before. It's as though I hadn't gone through the loop at all. So this is, and this was the intuition of a Markov situation, it's as though I haven't gone through the loop before. If I go through the loop again, and I'm at the start, it's as though I haven't gone through it before. If I go through it 10,000 times, it doesn't matter that I've gone through it 10,000 times. It's as though I'm entering it for the first time. So to get at the probability of exiting, we could just normalize. Normalize what? Here, I'm showing you this calculation. Uh-oh. So can you guys fill in the pluses and the minus? So we can simply compute the probability of exiting at x and the probability of exiting at y, and then compute the probability of staying in the loop versus exiting the loop, and normalize divided by the 2. So someone help me out here. It's going to be 1 minus p over 1 minus p plus p times 1 minus q. Okay, let me return to this when I have the arithmetic for the proper font and I explain it to you. But anyways, I'm certain this is correct. How about if I give this to you guys as a quiz to actually compute these for a different system? But the point is here that we can simply compute the probability of staying in the loop versus exiting the loop. We can either do it the way that Jacob suggested, which is set it up as an infinite sum, or we can just reason that the probability of staying in the loop is going to be one probability. The probability of exiting is going to be another probability. And reason what is the probability of staying in the loop at each iteration versus having exited at some point. Anyways, let me return to this properly since I'm stumbling a bit here. Okay. But here's the point that I want to make next. Suppose this was our state space. So suppose that we were following some simulation where each green dot was a potential point that we could visit in the state space. And we've noticed that there's a cycle. Perhaps we've gone through the cycle. We've gone through A to B to C, and we're back at A. Well, what we're doing here is we've computed two new probabilities. These probabilities are going to be the probability of directly exiting the cycle at X versus exiting at Y. But it's as though what we're doing is we're rewiring the state space. So instead of having this particular link that takes us on the cycle, what I'm doing is I'm directly adding two new lines in the state space. And the state space now, imagine, is a lattice of probabilities that are descending. And these two new lines have probabilities. And those are the probabilities directly from point A of exiting the cycle. Then what can I do with this information? So if I'm simulating this, the way that we were simulating stochastic systems, what can I do with this information? Yes, Ron?
So you break the cycle and go to X and say that as probability P, that any result that you get after that, you multiply by P. Include that in your distribution for M afterwards.
Sure. But in terms of what that's a good suggestion. But here, it's kind of a hybrid approach, because I'm not actually calculating probabilities. I'm simulating the system. I'm calculating probabilities in order to make a decision probabilistically on where I go next. So recall that the simulation paradigm is I'm at a given point. I've got a bunch of reactions that can occur. I compute the probability of each reaction being the next reaction. Then, based upon that probability calculation, I choose one of those reactions, I execute it, and then I keep going. That's what this trajectory is here. What I'm suggesting we can do here is follow that paradigm. So we're still simulating things stochastically, meaning we're still computing probabilities, making a choice, going there. Except when we're at state A, we can pretend that we have a reaction, as it were, that takes us to Sx directly versus a reaction that takes us to Sy directly. Yes?
So it's like you made a new reaction.
It's like you made a new reaction.
Yeah, but you just add the two reactions.
Yeah, exactly. So now, instead of here having just a single reaction that can take me from A to B, I have two reactions, one that can take me to Sx or Xy. And the key point is that I just calculate the probabilities of those, and that's what the formula is above there. It's messed up. It's just a calculation. It's the same kind of calculation that I had before, where based upon the quantities, I compute the probabilities of the two outcomes. So this suggests then that for stochastic simulation, what we can do is the following. Whenever we encounter a cycle, what does it mean when we encounter a cycle? Well, when we're following a trajectory through the state space like this, when we notice that we've come back to a place that we've been to before, then obviously there was a cycle. Then instead of potentially going through that cycle many, many more times, we can stop and perhaps go through the cycle one more time in terms of our algorithm, do the calculation that I showed you on the previous slide, which is not a complicated calculation. There's nothing really to calculate. It's just very simple arithmetic on the probabilities. Go through the cycle one more time, computing the probability of staying in the cycle versus exiting the cycle. And so in terms of the simulation, imagine that I'm a little man who's walking along. I should come up with a better analogy here. But a man who's walking along. He's rolling the dice and choosing where to go next. He's rolling the dice, he's choosing where to go next. He's rolling the dice, he's choosing where to go next. When he hits a cycle, he says, whoa. He stops rolling the dice for a second. And then he does a little bit of thinking. He says, all right, let me compute the probability of staying versus exiting. He works for a little bit. Once he's computed that, then he rewires the state space. So he's still standing right here in terms of his forward progress, but he's done a little bit of calculating to figure out where he should go next. And he rewires the state space, meaning he bends the rules. So he computes new probabilities, a new probability distribution for exiting to all these points. Then he rolls the dice, and he chooses one of those, and then he continues rolling the dice, and he chooses one of those, he rolls the dice, he chooses one of those. Yeah, John?
For this method, would you have to keep track of
very, very good.
time and the probability of how long it would take to get there? Is time something you want to keep track of, or is it not of interest?
That's an excellent question. It depends. It depends, but if you're keeping track of time, and this is what I've glossed over, I shouldn't gloss over it, because if you read Dan Gillespie's paper, he does not only the calculation of what is the probability of the next reaction to occur, but he does a calculation of what is the expected time for that reaction to occur. So he does both a calculation of, so he computes a probability distribution on what is the probability of every reaction being the next reaction to fire. And then he computes what is the expected time that it takes for the next reaction to occur. And that's also a probability distribution. He samples both. So he samples which reaction happens, and he samples how long it takes. So in essence, what he's doing in his simulation is he is computing time. For every step that you take in your simulation, you add a certain number of nanoseconds to your simulation. You keep going. So John's question is, well, if we've done this, we've lost the notion of time. We have, because in essence, we haven't calculated, or we don't care, how many times we've gone through the cycle. It could be once, or it could be 10,000. That was the short answer. The long answer is we can also calculate the time here. We just have to do the expected time calculation for staying on the cycle versus exiting the cycle. It means that we just have to do a little bit of advanced probability calculations to say what is the probability, the expected time that will stay on the cycle versus exiting the cycle. Yeah. Was there a question, Jason?
Yeah, I have a question, and I don't know if I just missed something a while ago. But why is it not, if we're trying to figure out where we end up, why is it not valid to end up in this loop? Why do we have to break from the loop? I understand we don't want to keep simulating.
Yeah, no, that's a very good question. So it's a valid thing to happen if we're limiting the amount of time. But suppose that we're saying the virus is going to choose one of the two outcomes. So it's going to keep going until one of two things happens. Suppose that thing happening is not in the cycle. So it means that we're allowing the simulation to run for an infinite amount of time, in principle. But then it becomes a mathematical question. Let's say you have a much higher probability of staying in the cycle versus exiting the cycle. Then do you ever exit the cycle? Could you stay in the cycle forever? Well, if there is a probability of exiting, even if it's low, then you will eventually take it. But it's a very good question, and both are very good questions. So what to do with time and what to do with exiting. But I thought that people were going to ask more about the algorithmic aspect of this. So, yeah?
Can I just think the red line, the red arrow, like this
Yeah.
diagram as a trend line on
Yeah. So, but this is exactly where I'm going. So imagine, I think I have, what comes next? Let's return to these caveats. But here, I just want to go through to the nice lattice picture that I have. Okay. So there's two notions. So there's the notion of the state space. The notion of the state space, this would be coordinates in n-dimensional space if we have n molecular types, each of which is a quantity or a concentration. We start at some concentration, some quantity, and or I should say quantity here. A reaction happens, we can go to some other set of quantities, and imagine this like a lattice that's extending down. Now, for each arrow in the lattice, we have a probability. So we have that probability descending all the way down. And what we're doing, because if you think of this, so here, the first question. On this slide, I'm not doing simulations, and the fonts are actually showing up. I'm doing calculations. How am I doing these calculations? I think it's obvious, but maybe not. So Tor, how did I calculate these probabilities here at the bottom?
So you took, there's only one path to get to that one on the left.
Perfect.
So you can just say you multiplied all of them, and then it looks like the one on the right, you just added up the possible paths.
Right, but why can we do that? And we'll explain what we've done. So what Tor suggested was that along a given path, we can just multiply the probabilities. I think that's obvious to us because of our knowledge of probability, that if we have a sequence of independent events, we can multiply the probability to get the overall probability of that specific sequence. But notice that we can have many paths that merge here. And this was based upon an actual set of reactions, that you can have paths that merge because you can, let's say, do reaction 1 followed by reaction 3, or do reaction 3 followed by reaction 1. That gets you to the same place, if you think of it. So if you have two possible paths that take you to the same place, then the probabilities are additive, the probabilities along the two paths. Because what's the probability of getting here? Well, it's the probability of taking this path versus taking that path. You add those two probabilities together. So it just becomes a lattice where probabilities are multiplicative along each path and are additive whenever the paths merge, and it just extends down. And in principle, this is all we have to do to calculate what's going on. We just have to calculate those probabilities. So keep multiplying them, keep adding them. As you guys will see when you tackle this problem in the next homework, it seems deceptively simple to do that. But this lattice grows, and the probability calculations that you have to do, especially with the merging of the paths, it gets to be a lot of probabilities. So this was the whole reason why, instead of just calculating the probabilities, we decided to simulate them. By simulate them, this is kind of the lazy man's approach to calculating probabilities. If you think of it, that's what so-called Monte Carlo simulations are. You want to compute the probability of an event happening. Me walking into a casino and walking out rich. I want to compute that probability. Well, in order to compute that probability, I should be able to compute what is the probability of me winning one hand or winning once at a slot machine. And then compute the probability of this happening repeatedly. And I could do that and just compute those probabilities, but it gets hard to do. So instead, what I do is I'm lazy, and I just simulate it. So I say I'm at this starting state. What is the probability of an event happening? I compute those probabilities, but then it's a random trial. So I just pick one outcome versus the other according to the probability distribution, go to that next state, compute the probabilities, go to that next state, do it until the end of my simulation, then repeat it 1,000 times. So these are two alternative ways, the lazy man's approach or the diligent man's approach to computing probabilities. Either simulate them or calculate them. But what am I actually suggesting with the cycles? I'm actually suggesting a hybrid method. So ignore this. But what I'm suggesting here is actually a hybrid method, where I'm not merely I'm mostly simulating, because I'm mostly doing the poor man's approach or the lazy man's approach, where I calculate probabilities, I choose a next state to go to, I go to that next state, I compute probabilities, I keep doing this. I'm mostly doing that, except that I'm doing some calculating. And the calculating that I'm doing is actually similar to the kind of calculations that I could do right at the outset. I'm computing what is the probability of going from here to there. So I'm computing what is the probability of going from here to there. But that suggests that I could be more creative of how I approach this hybrid concept. So first, this is probably where I should have started. I only have 2 minutes left. But let's discuss a little bit about the notion of sampling a probability distribution. Because if you guys had to write a program to do this, how would you sample a probability distribution? So what I mean by this is, suppose that I have 4 reactions now, R1, R2, and R3, and R4. And I've computed 4 probabilities in terms of what can happen. Well, if I'm writing the code to simulate this, what do I do next? So Ryan, what would you do next? Semicolon? Okay, and next line after the semicolon. So I keep saying sample the distribution, sample the distribution. What do I mean by that?
I'm guessing you mean compute, simulate it many times and see how many times you get to R1, R2, or 3, or 4.
But here I'm being much more explicit. So what do we do in this given step? Yeah, Ron?
This is like pretty crude, but what you can do in MATLAB is like generate a random
Yeah.
between 0 and 1. Then you can write, like, in this case, 4 if statements. So I give the numbers between 0
Perfect.
and 116.
Perfect.
R1.
Perfect. So without getting into the specifics of the language, that's not what we'll discuss. But exactly like Rowan suggested, what we'll do is, after computing the probabilities, we, to sample the distribution, we generate a random number. To generate the random number, that's a whole other topic. But in the code, we can use different techniques to generate a random number or a pseudo-random number. But we can generate a random number. Let's say the number we generate is between 0 and 1. If you're using a programming language, you often get an integer. So you have to divide the integer by the maximum range of the integer. But anyways, let's assume you have a random real number or floating point number between 0 and 1 that you get. The sampling of the distribution is obvious once someone has explained it to you, but perhaps not obvious until then. What does this mean? It means that we're going to get a random number between 0 and 1, but we don't have 4 equal probabilities. Or even if we did have 4 equal probabilities, what should we do? Well, exactly as Rowan suggested, we just lay out the probabilities on the line. So here, we would lay it out where we would have, this would be, for R1, we would go from 0 to 1/16. Then for R2, we would go from 1/16 to 1/8. And then for R3, we would go from 1/8 to 1/16. And then for R4, we would go from a quarter all the way to 1. So we divide out regions in the line from 0 to 1 based upon the probabilities. Then generating the random number, I liken it to throwing a dart. So throwing a dart, so this is the regions. So now I throw a dart. The dart is going to be...
Someone's phone's going off.
Yeah. I was once at the Guthrie Theater here. So just a stupid anecdote. I shouldn't waste time with this. But I had decided that I had to work on journal papers to get tenure. And I decided that I have to work on journal papers every day. So I set an alarm for 8 p.m., because that's the middle of my workday, where every day, no matter what I was doing, I had to stop and work on my journal papers, writing the journal papers. So I set this on the iPhone, but I set it as an alarm. And the alarm actually overrides the volume mute button. And even worse, I set the alarm to be the old horn alarm. It goes, and then I'm sitting in the 3rd row of the Guthrie that evening, not working on journal papers. I forgot all about it. I turned off the phone like I was supposed to. In the middle of the performance, the phone starts going off. And I was scrambling to get it because it was actually in a bag. And the actor, he actually stopped in the front row, and he glared at me until I turned off the phone. So horrible experience. All right. Here, for the random number generator. This is simple and obvious, but I think interesting. So what we do is, metaphorically, we generate a random number between 0 and 1. It's like throwing a dart. Imagine we throw a dart, but we throw the dart, and it's a dart that lands on a one-dimensional dartboard. But wherever it lands, if it lands here, then we choose the reaction that we've assigned to that interval. That's how we make the choice. So that's how we sample a probability distribution. It's just basically converting from a uniform distribution to specific probabilities. Okay. It's time, so let me stop here. At the beginning of next class, I'll properly explain to you the probability calculations and this idea of event leaping, and then turn to probabilities. Yes. Yes, please. Yeah.
Number 2, given a failure rate of
Given the failure rates
and of the gate, and you gave us 2.
Oh, that's.
So I'm a little bit confused about should we kind of develop the formula for the 2 questions? I mean,
I think this one. Yeah.